All right, last time we were talking about spring systems. And today we will continue with spring mass system and do some examples. Now we will consider the system with a forcing term. So this is system with mechanical system with a forcing term with a forcing term. Well, remember we had such a system. So there's a spring attached to a ceiling, and here there are some forces acting on this mass. We had restoring force by the spring, which is opposite to the direction of the movement. So this is Fs, which is given by, given by some constant times u. Okay. Oh, this upward direction is negative. Okay, so we will take negative of ku. And there is also a damping force. This is Fd, and this is proportional to the velocity, which is u prime. Okay, u prime. So u is here the position of the spring. The position. Okay. Now let's say there's one more force. There's also gravitational force, but it is equalized by, remember, k times L. K times L, the elongation distance. So we ignore that gravitational force. And different from the previous one, let's say there is also an external force in the direction of the movement. So this is F. This is the external force, okay? And this direction is positive and this is negative. So with all this, the equation becomes what? The total force, which is M, total force, let's say, or net force, let's say, this is the Newton's law, M times A, which is U double prime T, is equal to, so what are the forces here? We have minus gamma U prime minus K U plus F, okay? Or you can write in a better way like this, M U prime T plus gamma U prime. Let's just say here M U prime. Okay, U is a function of T, so we don't need to write T. gamma u prime plus ku is equal to f. F is a function, so it's not a constant. It's, let's say, f of t, okay? F of t. So we get a second order differential equation, non-homogeneous. Right-hand side is non-zero now, okay? And we will try to solve this. And remember, there are many ways to deal with it. You can either do it with undeterminate coefficients, or you can find annihilator. You can use the annihilator method, or you can use variation of parameters, right? There are several ways to deal with non-homogeneous differential equations. So let's do some examples. Do you have any question before we continue? Maybe let me remind here, this is spring constant. Okay, and here gamma is damping coefficient. Damping şey demek, söndürme gibi bir şey. Yani söndürme kuvveti oluyor. Dolayısıyla gamma çarpı u prime. Hareketi sönümleme gibi. Sönümleme daha doğru herhalde. Sönümleme kuvveti. Peki, all right, let's do this example. So we consider an undamped first, undamped spring mass. Undamped means gamma is equal to zero, basically, okay? So undamped means gamma is equal to zero. Spring mass system where 2 kilogram mass is attached. With the spring constant K is equal to 8 kilogram per second square. Okay, so we are given M and K. And let us do the following parts. So the following parts will be independent. Okay, following parts are independent questions about this spring system. The first part, A, let's say, suppose that the object is pulled 3 meters below the equilibrium position. And given an upward initial velocity, so that the resulting motion has an amplitude of 6 meters. The resulting motion has an amplitude of 6 meters. Find the position UT of the mass. Okay. So basically we pull down the mass, okay? We pull down the mass and then it moves up and down with an amplitude of 6 meters, and we will find the position function UT. And remember the spring mass here system with a spring constant K is equal to 8. And here we have 2 kilograms for the mass. K is this. So let's write down the equation. Let's write down the equation for this system. We have M is equal to 2, K is equal to 8. So this tells you that, well, gamma is equal to 0 because we don't have any damping, right? There's no damping. It's damped free. So this tells you basically 2 U prime plus 8 U is equal to 0. And there is no external force, okay? Here, in this case, no external force, basically, in that case. Well, let's solve this. You can simplify this and write the following. U double prime plus 4U is equal to 0. And the characteristic equation, P lambda, let's say, it's lambda squared plus 4 is equal to 0. And this tells you the roots are plus minus 2i. So this tells you lambda is equal to plus or minus 2i. And the solution here, it's going to be cosine 2t, sine 2t, right? So u of t will be c1 cosine 2t plus c2 sine 2t. Do you have any questions so far? We are not done yet. We will find C1 and C2 because we are given some more information here. Okay, so we're given that the amplitude is 6 meters. Remember the amplitude. Amplitude means basically, remember, it's like this. We have a graph like this, okay? All right. So basically, the amplitude is the distance between the top and the bottom points, okay? Half of the distance, okay? So this is 2a, okay? 2 times amplitude. And it's given by amplitude is, we did this last time, it's given by in polar coordinates, it's basically r, right? And remember, r was root c1 square plus c2 square. Here, c1 and c2 are the coefficients. We don't know what they are, but we will find out. This tells you what? This tells you basically, well, here, what is the initial position? We pull down the mass 3 meters below, right? That means the initial position is 3, and downward position is positive, so U0 is positive, right? U0 is equal to 3. U0 is equal to 3. What is U0? U0 is, when you plug 0 here, it's going to be C1 times cosine 0. Cosine 0 is 1 plus C2 times sine 0. Sine 0 is 0, so you will get C1. So we get that C1 is equal to 3. What about C2? Well, we know that amplitude is 6, so this is equal to 6, right? So from this, 36 is equal to 9 plus C2 square. That one. Okay. So from here, C2 is equal to, well, absolute value of C2 is equal to 3 root 3. So C2 is either 3 root 3 or minus 3 root 3. Which one? Well, what is C2? C2 is coming from the derivative. Let's check out the derivative, because derivative gives you the velocity. And here we are given the upward initial velocity. That means the velocity, initial velocity is negative, okay? Upward direction is negative. So U prime 0, this is the initial velocity. Soru mu var? Well, what is initial velocity here? The initial velocity here is, you find the derivative. Let's do it. Minus 2 C1 cosine 2t plus 2 C2, sorry, sine, it will be sine. Two cosine 2t, and you will compute this at t is equal to 0, which gives you basically 2, right? Okay, it's 2 times C2. And we know that initial velocity, it is velocity is upward direction is negative, okay? So it should be negative, upward, because of upward velocity, okay? Which tells you basically C2 is negative, so which tells you that C2 is equal to minus 3 root 3. So when you combine all this, we get that U of t is equal to, what was C1? C1 is 3 times cosine 2t minus 3 root 3 sine 2t, okay? Okay, how do we find C1? There is one question. C1 is coming from U0. U0 is equal to 3 because initial position is 3. You pull down 3 meters, okay? So from here, U0, what is U0? When you plug 0 here, okay? When you plug 0 here, you will get C1, okay? Clear? Any other question? Well, we are basically done with this part, but if you want to do, if you want to sketch the graph of this function, you can simplify this function, okay? Let us simplify this function. You can write it like this. You can take the 6 parentheses, and it will be like cosine 2t times 1 over 2 minus root 3 over 2 sine 2t. Why do I do this? Because now 1/2 and root 3 over 2, these are cosine of something, right? And sine of something. So you can write, for instance, this here is cosine pi over 3, and this is sine pi over 3. Sine pi over 3, which tells you that it's nothing but 6 times, so this is the cosine sum formula, 2t plus pi over 3. From this, you can see that the amplitude is 6, okay, it's clear, right? So this is the amplitude. What else? You can also see that the frequency is remember it is W0, which is root k over m, and it's equal to 2. And we see also this here, right? 2. It is the frequency. And what about the period? The period is the period of such a function. Remember, cosine is 2 pi periodic, but now cosine 2t, so it's going to be 2 pi over basically W0, which is W0 is 2, so 2 pi over 2, and this is pi. So it is pi periodic, so that means every pi you will get the same picture, okay? So if you shift the graph by pi, you will get the same copy of the graph, okay? Okay, any question with this part?
Yes, sorry, can I ask a question?
Sure.
I didn't get how we simplified and got 6 cosinus 2t plus pi divided by 3.
You didn't get which part? This part?
The simplification part. Yes,
Yeah, so we
simplification.
take 6 parentheses because 6 is the amplitude, okay? So at the end, you're going to get something like 6 times cosine or 6 times sine something. So 6 is the amplitude. And the rest is basically the cosine sum formula. It is, remember, the cosine A plus B is cosine A times cosine B minus sine A times sine B, okay? So we use this formula basically, okay?
Yeah, now I see. Thank you.
Okay, good. Any other question? All right, let's do the other parts. So let's continue this problem. Part B. Now suppose that there is an external force to this system. Suppose that a downward external force Ft, which is, let's say, cosine Wt acts on the object mass, where here, let's say the W here is, it's different from, let's say, W0, which is 2, okay? Which is different from the frequency of the system. And then find U of t. So there is an external force. W is a constant different from 2 and minus 2, let's say. Well, basically, since cosine is an even function, 2 or minus 2 doesn't make any difference, right? So let us find, in that case, the position when we have this external force. And this external force, it's not constant. We have a periodic force, right? Cosine Wt. So let's do it. Well, in that case, the equation becomes the following. Maybe just to simplify this, let's put here 2, okay? It's going to be easier to work with. 2 times cosine Wt. So we will have, remember the mass is 2u double prime plus the spring constant is 8 is equal to 2 times cosine Wt, okay? We're going to solve this, or you can simplify and write it as u double prime plus 4u is equal to cosine Wt. Here, to solve this, you can follow different ways. I will do it like first, I will solve the homogeneous part and find a particular solution, because the non-homogeneous part is easy to deal with. It's cosine function, so you can guess the form of the particular solution from this cosine, okay? So let us work with homogeneous part. We already worked with homogeneous part in the previous part, right? So it is u double prime plus 4u is equal to 0. And the characteristic equation is lambda squared plus 4 is equal to 0. And we had the roots. And from this, the solution of the homogeneous part is in the previous part. It's going to be C1 cosine 2t plus C2 sine 2t. Well, this part is different from the previous part. In the previous part, we pull down the spring and give some initial velocity and blah, blah. Here, We don't have anything like this. We have an external force, okay? So we don't know what C1 and C2 here. All right, let's continue with the particular solution. For particular solution, well, on the right-hand side, we have a cosine function, cosine WT. And cosine WT and W is different from 2, right? Here, W is different from 2. That means in the homogeneous part, we don't have the solution as cosine WT. And the particular solution will be Y particular is basically A times sine, or maybe let's start with cosine since we have cosine. A times cosine WT plus B times sine WT, and we will find out A and B. How do you do that? Well, basically, you will plug this in here equation, okay?
Bir soru sorabilir miyim hocam?
Tabii.
Burada particular solution'ı da cosine omega t yazdık ya. Hani bu mesela homogeneous solution'danla benzer olmadı değil mi? Yani ben t ile de çarpmak gibi bir şey düşünebilirdim buradan.
Eğer şey olsaydı, W2'ye eşit olsaydı burada, hani kosinüs 2 de homogeneous çözümün içinde olsaydı o zaman T ile çarpman gerekecekti.
Tamam hocam, teşekkürler.
Tamam. Yani homogeneous kısmı çözüyorsa o zaman evet çarpman gerekecekti. Bir sonraki aşamada onu yapacağız zaten.
Tamam hocam, teşekkürler.
So let us put this particular solution into, plug into star, and we need the second derivative. The first derivative, yp derivative, is why do I call y? It's u, right? Our function is u, sorry. This is u, and this is up prime. Up prime is minus a w sine wt plus b w cosine wt. And let us differentiate again because we need the second derivative. Up double prime is minus a w square cosine wt minus b w square sine wt. And let us plug this into star here, and we get 2 times u p double prime, which is 2 times minus a w square cosine wt minus b w square sine wt. Okay. Plus 8 times u, 8 times a, this. Okay. It's equal to what? 2 times cosine wt. Two times cosine wt. Well, we will equalize the coefficients of sine and cosine here. What is the coefficient of cosine? Let's see. minus 2 a w square. So we start with cosine, okay, cosine wt. So the coefficient of cosine wt comes from the first one and the second one, plus 8a is equal to 2. This is the first one. Now, let us write the coefficient of sine minus 2b w square plus 8b is equal to, on the right hand side, we don't have any sine functions, so this is going to be 0. But the nice thing is, this tells you in 2b parentheses, it's 4b minus w square. So this tells you that since w is not equal to, okay, this is 4, so right, okay. Since w is not equal to 2, this part is never 0. Since w is different from 2. Which tells you that b must be 0. And let us plug this back in. No, that's it. B is equal to 0. And from this, we can find A. A is what? In A parentheses, you will have 8 minus 2w squared. So 2 over 8 minus 2w squared, which is 1 over 4 minus w squared. That's it. Okay. Now, we know A and B. W is a constant, so we can plug back into the equation u of t, or maybe let's write like this. U of t is simply the homogeneous plus particular, okay, particular solution. The homogeneous part, remember, it was, where is it here? C1 and C2, right? C1 cosine t plus cosine 2t plus C2 sine 2t. And the particular solution is now, we know A and B. Remember, particular solution, A times cosine wt, 1 over 4 minus w squared times cosine wt, plus b times something, but b is 0, so that's it. Okay. So this is our particular solution, u sub p. And the general solution is given by the sum. And what you realize here is, let us look at the amplitude of this solution. The amplitude is basically the difference between the highest and lowest points, half of it. Well, it's almost like this number here, because from this part, the amplitude is simply like C1 or C2, right? It depends on C1 and C2, and they are constant. But if W is very close to 2, 1 over 4 minus W squared will be very, very large. So it will dominate the amplitude, right? 1 over 4 minus. It's almost like this if W is close to 2. It's not equal to 2, but if W is close to 2, 1 over 4 minus W squared will be very large. So the particular solution, the amplitude of the particular solution will dominate the amplitude of the general solution, okay? Well, what happens as W goes to 2? So as W goes to 2, the amplitude of U will approach to infinity, right? Because 1 over 4 minus W squared will approach to infinity. And this tells you simply that this behavior is called the resonance of the system. And this, let me write here, maybe in parentheses, this behavior is called resonance, okay? That means the amplitude is going to infinity. It becomes unbounded as W approaches to 2, and it causes the resonance. The picture, in the case of resonance, the picture will look like this, okay? So the amplitude will be large and large and large, okay? Like that. In that case, there is no resonance because W is not equal to 2, okay? But if you take W very close to 2, then the amplitude will be getting larger and larger. So in the case of W2, we have resonance. We will talk about this case as well. This is part C. We will talk about this. But do you have any questions so far? Buraya kadar var mı sorusu? Okay, maybe let's give a break here. For 10 minutes, let's continue at 11:35, okay? All right, welcome back. Let us continue with the third part here. Now we will consider the case of resonance when W is equal to 2 in the external force. Any question so far? Okay. So suppose that now, maybe let's open a new page. So suppose that the system is initially at rest. At rest. Well, that means u0 is equal to 0, and u prime 0 is also 0. The velocity is also 0, right? And a downward external force Ft, which is 2 times cosine 2t here acts on the object. Which causes resonance. Find u of t, okay? So now we will consider the case of an external force which causes a resonance here. It causes a resonance because of this here, W. W is equal to 2 now, okay? In that case, you will see that the amplitude will be very large. Okay, let's do it. Well, again, we start with the here equation of the system. It's 2u prime as in previous part. 8u is equal to 2 times cosine 2t, right? This is the equation. Now we will solve it. When we solve it, we first solve the homogeneous part. And as in the previous example, the homogeneous part is same. So u homogeneous is 2 times cosine, sorry, C1 times cosine 2t plus C2 times sine 2t, right? So this is the homogeneous part. Let's work with the particular solution. Particular solution UP. Well, here it's going to be different because the particular solution, this non-homogeneous part here, cosine 2t, is the solution of the homogeneous part. That means we need to multiply this with t to get the particular solution. So it's going to be a times t times cosine 2t, okay? So this is the solution of homogeneous part. That's why we need to multiply this with t plus b times t times sine 2t, and we try to find a and b from this. So let's plug this back into here star. First, we need to find second derivative of u. The first derivative is, well, it's going to be a little bit longer, minus 2a. We use here product rule. t sine 2t plus a times cosine 2t. Now we move to the second one, b times t times sine 2t. 2bt cosine 2t plus b sine 2t, right? This is the derivative. We differentiate this again and find the second derivative. Up double prime is what? Well, it's going to be minus 4a t cosine 2t minus 2a sine 2t, but there is also here from this derivative there is another minus 2a sine 2t. So when you combine this, you will get that minus 4a sine 2t. So now we are here, okay, this part, derivative with respect to t. So we use product rule again. It's going to be, well, again, it's going to be negative. Minus 4b t sine 2t. And again, 2b cosine 2t, and there is another 2b cosine 2t here. So it's going to be 4b cosine 2t, okay? Now let us put this back into star. So plug in star, and we get what? Well, 2 times up double prime plus 8 times u. Well, there are going to be some cancellations. You can see this easily. For instance, when you multiply u double prime with 2, it's going to be minus 8a t cosine 2t. And when you multiply this with 8 up, it's going to be 8at cosine 2t. So they will cancel, okay? So after this cancellations, you will end up with minus 8a sine 2t plus 8b cosine 2t. You can check this easily, okay? And it's going to be equal to 2 times right hand side, 2 times cosine 2t, which tells you basically minus 8a is equal to 0 and 8b is equal to 2. So a is equal to 0 and b is equal to 1 over 4. Let us put this back into up. So up is, the particular solution is, a is 0, b is this, okay, 1 over 4. So t over, or t times sine 2t over 4. Okay. So the general solution is u of t is basically c1 cosine 2t plus c2 sine 2t plus the particular solution, which is t times sine 2t over 4. We also have the initial conditions. Remember the initial conditions here. u0 is equal to 0 and u prime 0 is equal to 0. So let us put this here to find c1 and c2. So U0 is what? U0 is when you plug 0, sine will vanish. So you will end up with C1, and this is equal to 0. U prime 0, when you plug 0 into the derivative, it's going to be derivative of cosine is sine, so this will vanish. There's going to be here 2 times C2 times cosine 0. Cosine 0 is 1. And this derivative of this will vanish at 0. You can check this easily. Okay. So we get that. We get what? This is equal to 0, which implies C2 is also 0. Well, this tells you simply UT is T times sine 2T over 4. Okay. So this is the solution. Well, this causes a resonance. You can see this easily from the formula, because as t goes to infinity, right, this will approach to infinity plus minus infinity, because sine is either positive or negative, right? So the graph will look like the following. This. At 0, it is 0. And as t goes to infinity, it goes up and down with sine. It's like that. And continues like this. So you see here, well, this is basically, if you look at this line here, it's like, this is t over 4, okay? T over 4. Okay. Or maybe let's say not ut, it's y is equal to t over 4. And this is like minus t over 4, okay? So it oscillates between t over 4 and minus t over 4, and this is your ut. Okay? And this is the case of resonance. You see as t goes to infinity, amplitude gets large and large. Any question so far? Var mı soru arkadaşlar buraya kadar?
Hocam ben bir şey sorabilir miyim?
Tabii.
Yukarıda U partikülleri yazarken ilk başta neden o şekilde yazdık? Açıklar mısınız?
Bunu daha önce yapmıştık. Yani şey olunca, particular solution, homogeneous solution'un içinde olunca o zaman bir t ile çarpmamız gerekiyordu.
Evet, tamam, teşekkür.
Çünkü şu şekilde t'siz halini koyduğun zaman denkleme bu taraf sıfırlayacak. Oradan şeyi bulamazsın, değil mi? Constant bulamazsın.
Doğru, tamam, teşekkür.
Any other question?
If I'm not mistaken, the friend asked the question I wanted to ask, but I want to listen this in English. Like,
Right,
why
so-
we multiplied by t?
Right.
T.
The reason is the right-hand side is the solution of the homogeneous part. So if you try this, for instance, without t, okay, if you try this, the right-hand side will be 0. And this will not give you a and b in that case, right?
Yeah, I got it. Thank you.
Because cosine 2t is the solution of the homogeneous part. So if right-hand side is the solution of the homogeneous part, so to get the particular solution, we try next one, which is more similar to cosine 2t, and this is going to be t times cosine 2t, okay?
Thanks.
Yeah. All right, good. Well, there are other ways to deal with this sort of equations, non-homogeneous equation. You can try, for instance, annihilator method, because we know the annihilator of cosine 2t, right? So you can try annihilator and you will get the same answer. or you can try variation of parameters, which is more complicated than this. Okay, any other question, comment? All right, maybe let's move to a new section, new chapter. So we're done with basically mechanical systems. So let us move to chapter 5. And we will start with maybe power series method. Let's say power series solution, let's say. So our purpose here, our goal here, we will solve such an equation, px times y double prime, non-constant coefficient. Okay, we have non-constant coefficient px and another qx, and y prime and rx, y is equal to fx. So it's a second order equation with not necessarily constant coefficient. Okay, and using power series. Okay, so we're going to write the solution y, and the power series form like this: an x minus x naught to the n is from 0 to infinity. Remember this from calculus. As a power series is a function in the interval of convergence. So let me remind maybe those terms. What's an interval of convergence, radius of convergence, and so on. So let us review. This is 5.1, review of power series. Well, so let us recall this from calculus, the radius of convergence. What's the radius of convergence? Well, when we have a power series like this, for power series an x minus x0 to the n is from 0 to infinity, there exists a real number. Let's say rho such that 1, the series is convergent absolutely. Absolutely means, remember, you take the absolute value of the terms of the series and it is convergent. So it is strongest convergent convergence. Absolutely for all x such that x minus x naught is less than rho. Okay. And second, it is divergent outside of the interval. The series is. I will explain this with geometry. Okay, you get it better. The series is divergent for all x such that x minus x naught is bigger than rho. Okay, then this rho is called well, I should say this can be 0 as well. Okay, rho is called the radius of convergence. Okay, the radius of convergence. So what I'm saying is, well, let's say you have the center here, x naught, okay, and nearby the center, we find an interval with radius r, radius rho. So this is like x0 plus rho, and here we have x0 minus rho. Okay, so in the interval, this interval, we have absolute convergence. Outside, the series is divergent. So when x is outside, the series is divergent. Inside, it is convergent, and it's absolutely convergent. At the endpoints, you may have a divergent or convergent series. Endpoints are not clear. You need to check endpoints separate. So endpoints, we don't know what happens in general. It depends on the series. So you need to check endpoints separate. Inside, absolute convergence. And outside, here, we have divergent series. Okay. And this interval is called interval of convergence. This interval is I is, which is x, x0 minus rho and x0 plus rho. Well, depending on the endpoints, you may include or exclude. So sometimes we have this, okay. It depends on the, or maybe let's write it, not for the confusion here. It may be like this. Or this. Okay, or it can be like this and so on. Anyway, so it's called, so I is the interval of convergence, okay? Do you have any question so far? Well, let's do some examples. So you may remember all this from calculus, right? Let us find the center, find the center, radius, and interval of convergence of the series 2x plus 1 over, sorry, to the n over n square. Okay. Well, this series is not in the form of power series. First, we will put this in power series PS form and then find the center, radius, and interval of convergence. What is the center? Can you guess the center?
-1/2.
Okay, good. It's -1/2 because you can write this as this. Take 2 out, it's going to be 2 to the n over n squared. What is left? Well, when you take 2 out, it's going to be x plus 1/2 to the n. Okay? So you see that -1/2 is your center. Center C. Okay? Because this is like x minus -1/2. Well, let us find the radius of convergence. There are different ways to deal with this radius of convergence. We will use ratio test. You can also apply ratio test in different ways. I will prefer this way. I will say the whole thing here is, let's call it Bn, okay? And so to find the radius of convergence, we use a ratio test to Bn, okay? Which tells you basically the limit of Bn plus 1 over Bn in absolute value, okay? Let's write this better. This should be less than 1 in absolute value, okay? So it's going to be this. Over n plus 1 square times n square 2x plus 1 to the n. Forgot the limit here. As n goes to infinity. I don't write n goes to infinity, but when we're talking about sequences, n always goes to infinity. What is this limit? Well, we can simplify a little bit. So it's going to be limit, absolute value here, 2x plus 1. So when you simplify with this, n squared over n plus 1 squared. But the nice thing is the limit of n squared over n plus 1 squared is 1. So you're left with 2x plus 1. And you want this to be less than 1 in ratio test, right? For convergence, we need this. This must be less than 1. Convergence in ratio test. Okay, well, it tells you basically what? It tells you that 2x plus 1 is between 1 and minus 1, and 2x is between 0 n minus 2. So x is between 0 and minus 1. We are almost done. Well, basically, let me say here a few words. What is the radius here? Well, the radius is 1/2. Okay, it's you can see from here because you can think of this here. It's this same thing with this, right? X plus 1/2. Minus 1/2 is the center. It's less than 1/2. That means this is the radius of convergence. Okay, radius of convergence R. For interval of convergence, we need to check the endpoints. Let us check the endpoints. X is equal to minus 1. When x is equal to minus 1, let's see what happens with the series. When you plug here minus 1, you will get minus 2 plus 1, which is minus 1. We get this series, minus 1 to the n over n square. Well, this series is it convergent?
No,
Why not?
it oscillates between, I think, up and down, minus 1 and 1.
Yes, but here, right, it goes up and down, but it also converges to 0, right?
Okay. Yeah.
That doesn't tell you that it's convergent. Remember, the main term may go to 0, but series can be still divergent. But here, this is absolutely convergent because is absolutely convergent. Why is it absolutely convergent? Because when you take the absolute value here, n square, the absolute value, this is nothing but 1/n square, and 1/n square is convergent by p-test, right? Is convergent by p. Here p is equal to 2. Remember, when p is bigger than 1, it is convergent, okay? So you need to remove some calculus here, okay? This is your p. And we know that if your series is absolutely convergent, it is convergent. Absolute convergence is much more stronger than convergence.
Sorry, can I ask a question before we go forward?
Yeah,
Limit n goes to where?
n goes to infinity always.
Okay, thank you.
It's a sequence. In sequences, n always goes to infinity. I guess you're talking about this, right?
Yeah, there was only limit n. I didn't understand where it goes.
Yeah, n goes, because these are sequences. In sequences, n goes to infinity. Okay, well, infinity. Okay. Any other question? Well, what about the other endpoint? The other endpoint is x is equal to 0. When x is equal to 0, we have, remember the series here. Well, when x is equal to 0, it is 1/n square. And 1/n square is also convergent. Is convergent. Which tells you basically endpoints are included in the interval of convergence. It's because the series is convergent at both endpoints. So the interval of convergence is basically minus 1 to 0. Okay, that's a closed interval. Any question? Any comment? Okay, well, now let us talk about some examples of power series. Some well-known power series. Again, you should remember this from calculus. The exponential function e to the x, remember it was x to the n over n factorial. N is from 0 to infinity. That means it is basically 1 plus x squared over 2 factorial, which is 2, x cubed over 3 factorial, and so on. This is exponential function. Sine function, sine x, it's, remember, it's an odd function, and we have odd powers. You can remember the formula from this, minus 1 to the n, and x to the 2n plus 1, odd powers, and here 2n plus 1 factorial, n is from 0 to infinity. That means you start with x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus blah, blah, blah. Cosine x, it's an even function, so you will have even powers in the expansion, power series expansion. Again, minus 1 to the n. It's an alternating series. These are sine and cosine. They are alternating series, okay? It alternates between plus and minus. X to the 2n over 2n factorial. And this is nothing but when n is equal to 0, you get basically 1, right? It's like 1 minus x squared over 4 factorial plus x to the 6, sorry, 2 factorial. When n is equal to 1, you get this. N is equal to 2, you get 4. Factorial, and so on. Okay, so these are the expansions of sine and cosine and exponential. We will use this later, these expansions. Let us define an analytic function. You also remember this from calculus definition. What is an analytic function? Well, an analytic function is a function which has the power series expansion, which is equal to the function itself. Okay, a function f of x is called analytic at a point x naught if there is a neighborhood if there is a neighborhood of x naught in which the power series, the Taylor series, let's say, I will define Taylor series now. Taylor series is a spatial power series where the coefficients are coming from the function, derivatives of the function. The Taylor series is this. The coefficients are coming from the derivatives of the function at x naught. Okay. X minus x naught to the n is from 0 to infinity, converts to f of x. Okay. So if the Taylor series of the function is equal to the function itself in a neighborhood of the center, then you say the function is analytic at that point. And we know again from calculus, sine, cosine, exponential, these are all analytic functions. They are, I mean, most functions are analytic in calculus, but there are also functions which are not analytic. Right. So let us recall this fact. Exponential sine x, cosine x, polynomials, they are analytic at any point in the set of real numbers, are analytic everywhere, let's see, analytic everywhere. What about rational functions? Rational functions, it's a function of the quotient of two polynomials like p of x over q of x. Here p and q are polynomials where p, q are polynomials. So it's a rational function. R is rational. Is analytic at any point x naught where q of x naught is not equal to 0. Okay, so if the bottom doesn't vanish, then you have again an analytic function. All right. Well, now let us talk about, this is 5.2 and 5.3, series solution near an ordinary point. Series solutions near an ordinary point. what is an ordinary point? Let's define this first. So let us consider a differential equation. We want to solve it. So it's like px y double prime plus qx y prime plus rx y is equal to 0. So this is my differential equation. I can rewrite this as the following. If p is not identically 0, so we can assume that p is not identically 0, okay? It can be 0 at some points, but it's not all 0, okay? In that case, we can write this as y double prime plus q of x over p of x y prime plus r of x. P, Q, R are some functions. They are not necessarily polynomials, okay? Here. They can be any functions. Any function here. And this y is equal to 0. And you will like to solve this equation. But let's define what's an ordinary point first, the definition. Well, an ordinary point is a point where this here, the coefficients are analytic at that point. Okay, so a point x naught is an ordinary point of, let's say here, star, okay, if q over p and r over p, these are functions now. They are both analytic at x naught, okay? If one of them at least fails to be analytic, then it's not ordinary point. We call it singular point, but it's not very important, okay? Or maybe let's write it here. Otherwise, x0 is called singular point. So if one of them fails to be analytic, then we say this point is a singular point. So we have either ordinary point or singular point, right? Well, let's write this remark first, then we will do an example. Or maybe let's write the remark and we will stop. Around an ordinary point of star to find a power series solution, substitute y is equal to an x minus x0 to the n is from 0 to infinity. So x0 is an ordinary point of the equation. Then you take this power series and you substitute this to the equation, and by doing this you can find the coefficients a n. So that means you will find the solution in the power series form. We will do an example next time in class and find the power series solution. So let us stop here. Any question, comment?
Hocam
Alright.
bunlar bir şey sorabilir miyim?
Sor.
Bunlar hocam o zaman yine böyle ikinci dereceden ya da yüksek böyle üçüncü dereceden high order'ları çözmek için mi, yoksa sadece hani böyle ikinci türevi dedik ya, sadece o formda mı olacak?
Aslında yüksek dereceli şeyleri de çözebilirsin ama o zaman çözmek bayağı zor oluyor. Yani ikinci derecede bile bayağı bir o koefficientleri bulmak bir iş. O yüzden biz genelde ikinci derece yapacağız ama yani sadece ikinci derecede sınırlı değil tabii ki.
Tamam.
Ama biz orada kendimizi şey yapacağız. Yani ama bu metot şeyde kullanılabilir. Daha yüksek derecelerde kullanılabilir.
Yani higher order linear differential equation'ın çözümünde
Evet.
serilerin kullanımı.
Evet,
Başka bir yönteme geçtik. Tamam.
Evet, yani buradaki şey ama koefficientlar sabit değil. Kritik olan o. Yani koefficientlar sabit olmak zorunda değil daha doğrusu. Değil mi? Zaten koefficientlar sabit, hani biraz daha şeyimiz kolaydı. İşte orada farklı yöntemler vardı. Şimdi bu durumda işte coefficient, mesela bakayım örneğimize.
Orada 2, 8 falan vardı.
Evet,
Burada
mesela şey,
Sabit olmayan dediniz y'ye bağlı mı?
yok, x'e bağlı. Koefficientlar yine x'e bağlı. Şimdi
linear.
şurada. Evet. Yani biz higher order'larda koefficientları hep sabit alıyorduk ya, çünkü karakteristik denklemi falan buluyorsun değil mi? Bir önceki örneklerde higher order'da ikinci dereceden denklemlerde şunlar hep sabit oluyordu, sabit sayılar. Şimdi mesela bu şey olabilir, işte x kare sinüs x falan gibi şeyler olabilir.
Tamam
O zaman
hocam.
bir şeyi kullanamıyorsun, karakteristik denklemi falan yazamıyorsun çünkü o, değil mi? Sabit durumda yazabiliyor. Peki.
Evet hocam. Teşekkürler.
Oldu mu?
Oldu hocam. Teşekkürler.
Var mı başka soru?
Benim
Yine
yok hocam.
all right. Let me write the example, and next time we will solve this. For instance, y double prime minus x times y is equal to 0 around x naught, which is the origin. Okay, so we will solve this equation nearby the origin. Okay, see you on Friday. Bye.
İyi
İyi
günler
günler
hocam.
hocam.
Görüşürüz.